But before we get to that, I just want to say, I see we already have a couple questions in the chat, but we're going to get to those at the end. So just letting you know, I see them and we'll wrap around at the end to address those. But without further ado, Gaylord, I'm going to leave the floor to you.
Okay, thank you, Shane. Yeah, my name is Gaylord Olson, and I'm an engineer. I live in Princeton, New Jersey, and I've been working with some other engineers locally and elsewhere in the country on some different kinds of heat pumps and underground thermal storage as well. They kind of tie together. What you have on the screen now is kind of a blurry example of what would be called a multi-source heat pump. And this is kind of an extension of what people usually have outside of their home right now, which is a central air conditioner box. So instead of only being a central air conditioner for cooling, a heat pump has what's called a reversing valve internally so that it can be a heater or a cooler, whichever you need at the time. In this case, it's a multi-source heat pump. It's got an air source element at the top, which is it's got a fan and it's got a coil with refrigerant in it. And that is an air to refrigerant heat exchanger. And that's the basic element of anybody's outdoor condenser box for a central air conditioner. So this also has a ground loop near the bottom left. The vertical little rectangles are supposed to be examples of boreholes drilled into your yard. And they have pipes that go down and back up, which contain water or antifreeze solution, kind of like the radiator solution in your car. And then there's a water pump. The little round thing with the triangle is a symbol for a water pump. So basically there's a ground loop here, and the ground has relatively stable temperature all year long compared to the air. So during extreme temperature conditions, the middle of the summer when it's really hot, the ground is a better choice. You get higher efficiency when you have a temperature on the source side of this box compared to what you need for the inside of the building. I should explain also, DHW near the top in the box is domestic hot water. So that supplies the hot water for your showers, your laundry, etc. And again, there are water pumps with the little circles and the triangles showing to the right. Where it says user, that means space heating and space cooling. It keeps the rooms in your house warm or cold, whatever you need. So basically, this has two sources, air or ground or water. And this is a more versatile. The image here was taken directly from a document that was published by a number of Spanish authors a few years ago. And at the end of this talk, I have my contact information, and I'll be able to send out the full details on anything I'm talking about here. Basically, there are two documents that contain all the details. One is from 2 years ago, and one is from just earlier this year. The one from this year, I believe, will be published in the archives of the festival that we're all attending right now. But I can also send it out to anybody who is interested. So I think we'll move along. Well, I should also add the future of heating and cooling of buildings. There are people working on what's called renewable natural gas. And so they might want to convince a lot of people that, no, we shouldn't get rid of our gas lines. We should just have a different, better form of flammable gas coming in to our homes. or heaven forbid, hydrogen. But if you think hydrogen is a good idea, I would suggest you take another look at the videos of Hindenburg right here in New Jersey. Watch that a few more times, and you might convince yourself that you do not want hydrogen coming into your home. At least that's how I feel. So basically, if it's not going to be a flammable gas, it's probably going to be all electricity to do everything you need. And heat pumps are definitely a good idea, and a lot of people are moving strictly towards air source heat pumps. In other words, there's no ground connection. And that's okay for some homes, maybe, but there's a great concern that if everybody only had air source heat pumps in 10 or 20 years, we'd have an overload of the power grid, because on the hottest summer afternoons, everybody's got a very low efficiency for cooling their building. And even worse, on the very coldest winter nights, there's even a worse efficiency and a higher electricity load on the power grid. And I think the only two options away from that are to spend a lot of money building more power lines to come into everybody's communities, or else have a very high price for the electricity. So people would be discouraged from using so much of it. So to avoid that, if the heating and cooling has a ground loop, that problem is totally taken care of. So that's an argument not to rely totally on only air source heat pumps. Now, there are certainly a lot of people promoting ground source heat pumps. And right now in this country, that's usually the choice. If you want to buy a heat pump, people will say, well, do you want a ground source type or do you want an air source type? In Germany right now, there's another choice. You can buy a multi-source heat pump from a company called ThermSelect. And if you go to their website, what you'll see in big, bold print right on the home page, the most efficient heat pump in the world. It's more efficient than ground source heat pumps and much more efficient than strictly air source heat pumps. And by efficiency, what I mean is for a given amount of dollars to install the system, the electricity use for a given building, a given amount of load will be actually lower than any other heat pump. And I think they have a legitimate claim for that promotion. In this country, there may be one company that's offering a multi-source option, but not in a single box like this example shows. I've got to watch the time here so I don't spend half the talk on one slide. So I'm going to move along now. I hope. I press the advance button. I guess there's a time delay. Oh, wait a minute. What? I'm not able to advance the screen. Oh, there it goes. I just had to click somewhere else. I don't know how that happened. Anyway, here's another example of a multi-source heat pump. And this was a design done by people in Italy. And in this case, there's no air source mode at all, but instead the multi-source comes about from a solar thermal collector. And if you attended the first talk in this session today, you would have learned a little bit about solar thermal collection. So that's at the upper left here. And the solar heat feeds into a buffer water tank. And then there's a heat pump for a building. And again, you see a number of water pumps. And the other symbols there with the letter Z or whatever, those are special types of one-way valves. But anyway, there are borehole heat exchangers. Again, drilling into the ground and putting in plastic pipe where water goes down on one side and comes back up on the other side. So the heat pump in this building has a choice of water that comes from the solar thermal collection or water from the borehole heat exchangers. This design has another very good feature, which is that in the summer, when it's really hot and the sunshine is very, very strong, the building doesn't need any more heat. It's got plenty of heat. So what do? Here's what you do. You turn that pump number 3 on and you pump really nice warm water into the borehole heat exchanger loop. So now you're warming up the dirt all around the borehole, or boreholes, plural. So now, and this design is specifically for cold climates, actually. So they've got nice warm dirt in December and January to give warm water for the heat pump. Guess what? That makes it very efficient compared to air source or anything else. So if the sun doesn't shine for a week, no problem. They've got plenty of warm water from the ground loop. So the heat pump provides nice, efficient heating for the building. So this is a pretty good design, I think. Again, no air source mode, but solar thermal, ground source, and multi-source. Now I've got to figure out how to advance to the next slide. Just click and it advances. What wonderful. This is another example of what would be called multi-source, and it comes from 3 authors in Belgium. But this is much different in that even though it has something called a dry cooler, and I'll explain, a dry cooler is nothing more than an air to liquid heat exchanger. It's got a fan. It's the same thing as the radiator in your car. It's got water or antifreeze solution. It blows air across the fins and tubing inside of the device. And so heat from the air will be transferred into the water or antifreeze, or cold air will transfer cooling there. So it's bidirectional. The word cooler is really a misnomer. It's an air to liquid heat exchanger, whether it's doing cooling or heating. So here's what's going on with this example. The dry cooler doesn't have any way to feed into the heat pump in this design, but the dry cooler plays a very useful role. It's used in the extreme temperature conditions of summer and winter to do preconditioning of what they call the bore field. Bore field being a bunch of boreholes with plastic pipe embedded in them. So you'll see here on the left, the dry cooler is being used only to precondition the left-hand bore field. It's got red because that's supposed to indicate hot. At the same time, this is being a very hot summer afternoon. There's cold water from the right-hand bore field that feeds into the system, and it could feed directly through the heat pump if necessary. But if the temperature of that water from the cold bore field is low enough, then you don't have to even use the heat pump. So they're showing a pair of valves that redirect the water around the heat pump, bypassing it. So that's extremely efficient cooling. The cooling is done by the use of only water pumps. So on the right-hand side of this example is the opposite season. It's now the coldest night of the winter. So the dry cooler is feeding nice cold water into the right-hand bore field to make it as cold as possible. And at the same time, you've got nice warm water from the left-hand bore field feeding up. In this case, it's using the heat pump. And the heat pump has a compressor which takes some electricity. So the electricity into the heat pump and the warm water together provide the heat for the building. Now, what we're not showing in any of these examples is what's going on inside of the building. And of course, that can be a number of different designs. It could be ductwork, where air is blowing into the ducts into the different rooms of the building. It could be what's called hydronic, where you have water that is distributed in pipes through the building. Or it could be refrigerant pipes, which are very small diameter copper pipes that have refrigerant that goes into different rooms of the building. So all of that is industry standard, and we're not showing anything different for that part of it. And likewise, the heat pump in all of these examples is a common mass-produced off-the-shelf water source heat pump. There are actually 3 names for that. Water source is one name, Geothermal heat pump is another name, and ground source heat pump is a third name. They're all the same thing, except with slightly different temperature ranges, perhaps. All right, so we have examples now from Spain, from Italy, and from Belgium. And the example from Spain is shown here in a very crude way on the left. The heat pump has a choice of fluid, either from the dry cooler or from the ground loop, whichever is better at the time. On the other hand, the system from Belgium does not have the ability to have the dry cooler output going to the heat pump. What it does have is the ability to precondition either the hot loop on the left or the cold loop on the right. Now, wouldn't it be kind of good if we could combine these effects together in one system? And I think it is possible. And that's what we are going to show on the next slide. That it works. So here's an example which is quite a bit simpler in terms of the number of valves that we had for the Belgian design. It does have 2 water pumps, and it has 3 valves. The things with the triangles are 3-way valves, and everything is going to be computer controlled here. We'll be able to control the pump, flow rate for those 2 pumps individually, and we're going to control the valve settings so water can flow from one side to any of the other sides on those valves. So now we have 2 underground regions. We've got something called an above ground thermal exchange unit, and we gave it that name because it could be a solar thermal collector, it could be an air to liquid heat exchanger, or a combination of those things. But in general, it's meant to be something above ground that has either warm or cold water that can be fed into the system. So moving along, here's an example of settings of the valves to show what's going on in the coldest winter night. This follows the example of the system from Belgium. So what we're doing is we've got very cold water from the above ground unit feeding into the left-hand ground loop. We got nice warm water from the right-hand loop feeding into the heat pump, giving very efficient heating for the building. On the opposite season, on the hottest summer afternoon, we're taking nice warm or maybe even hot water from the above ground unit, feeding it into the right-hand ground loop. And we're taking nice cool or cold water from the left-hand ground loop, feeding it through the heat pump to get efficient cooling for the building. So that kind of gives the benefit of what we were showing from the authors in Belgium. Now, if we want to, we can do what's called a parallel mode, and that's what this is. If you have a temperature from the above ground unit, which is very similar to the temperature from the one of the units above below ground, you can have part of the water coming from both of them. And to keep it simple, you might have the same water flow from both the bottom unit and the right-hand unit. To do that, all you have to do here is control the top water pump to have twice the flow rate of the bottom water pump. And in that case, the same amount of flow will be coming from both blocks, the right-hand one and the left-hand one. And this is strictly for heating. You can do the same thing strictly for cooling. In this case, we're getting an equal, if we want, we can get an equal flow rate from the left-hand block and from the above ground block at the bottom. Now, the benefit of that parallel mode shows up here graphically. I think I'm okay in terms of time. So this graph shows three different conditions for the valves and pumps that we were describing earlier. And this shows the example where the building needs to be heated. And if you have an air source heat pump, then what you've got is the 45-degree angle line that's called real world dry cooler there. And that would follow all the way down to the bottom left, which means you're going to have really cold water for the heat pump, even though you're trying to get heat for your building. That is extremely inefficient. That is, let's see, if I move my mouse around, Shane, can you see where my mouse is pointed right now?
Yeah, we can see it.
Oh, okay. So anyway, if you have just an air source heat pump, then you're going to be along this line right here. So if you're trying to heat your building, okay, well, I should explain. Source fluid temperature, this is what's coming into the heat pump. Ambient air temperature, that's what the air temperature is outside. So basically right here is the freezing point for the ambient air, 32 degrees Fahrenheit. So now you'd be coming down here where most of us live. We can get down to pretty much zero or even below. So that's way down here. We'd have an extremely low efficiency for the heat pump if we had to depend on only this line right here. No good. So basically, instead of that, if we have a ground loop, we can operate up here. So what we're saying is when the temperature is very low for the outdoor air, we have a ground loop which feeds, in this case, is not very warm. What we're showing is about a 36-degree Fahrenheit plus 36-degree Fahrenheit temperature for the water that can come into the heat pump. That's still reasonably good efficiency compared to way down here of zero or something. So now, if we do not have the parallel mode, we would be coming along this horizontal line and we'd come all the way up to here. And then the computer would say, we're better off switching now to an air source mode. So then we'd move right up to here and we'd move up this line. And so now we're getting warmer and warmer temperature. Up in this region, we're better off using the air source mode because the ground temperature is still down here at 36. So if we want to get heat for our building, and we're right here at a 55-degree Fahrenheit outdoor air, people are usually not comfortable in a building that's at 55 degrees Fahrenheit, so we need some heating. So let's use the air source mode, which is right here where my mouse cursor is pointed. So that's going to give a much better result than only the ground loop. If we're right here at an ambient temperature of, let's say, 44 degrees Fahrenheit, if we use the parallel mode, we're not stuck with 36 degrees Fahrenheit for the heat pump. We can go up to 40 degrees Fahrenheit. So we get a boost of temperature from using that parallel mode. That's why it's put in there. And the colors here just indicate right up here, the parallel mode with equal flow rates from both blocks. That's the red line. If we have totally variable flow rates, we can do a little bit better than that. That's the green curved line here. So, but the bottom line is we have three different modes capable of choosing. The ground source mode when it's very cold, the parallel mode in the intermediate region, and we have an air source mode all the way up here. Of course, when we get up to 70 or higher for the ambient temperature, we don't need to use the heat pump at all. We just open the windows. Now, this same type of result would show up on the graph way up here off to the right, except that's the example where we need cooling for the building rather than heating. So I guess I've spent enough time on this one. I think I'll move along. to the next one. So when we go to the air source mode, the connections and the flow are as shown in this graph. Neither of the ground loops are in operation, or in use, I should say. We have the flow equal from the two water pumps. So it's a counterclockwise. The arrow indicates direction of flow, actually. So we have water flow coming up this way, coming down this way, and these two valves are set. So we do not allow any flow horizontally into this block or the left-hand block. Now, if it happens that somebody already has a ground loop installed for their building, let's say with a ground source heat pump, or if they absolutely have no way to get other than one ground loop, there's a way to handle that, and it becomes much simpler. And that's shown in this this slide. Now, there are still 4 different modes operable for this system. The ground source mode, where we use only the right-hand block flowing through the valve this way. The air source mode, where we only have flow going up this way and back down through the above ground unit. Of course, that could be solar thermal or air to liquid exchange or whatever. We also have the parallel mode, where if the flow rate in this top pump is twice the flow rate of what's in the bottom pump, then we will have an equal flow from the right-hand block and from the above ground block here. And there's also a preconditioning mode. If the building does not need any heat at all, this top pump would be just turned off. The heat pump is turned off, but we can still do what we call preconditioning with water flow up from the bottom pump. Let's see, what am I trying to say here? Yeah, okay, water would flow up from the bottom pump through this valve, through this block, back through this path, and down this way. So Shane, you see my mouse cursor still?
Yep.
Is that still visible? Okay, all right, I'm glad that works. It would be nice if I could allow for questions at any time here, but I think that's not what's going on with this presentation, right? I shouldn't interrupt and ask for questions.
I think we'll just save them for the end, just to make it easier.
No problem. So now suppose that somebody has a large building, or suppose you want to simultaneously have water fed into a number of buildings in a community or a campus. How would that work? Anyway, this is an example of that. So here, instead of a single heat pump, we're showing 15 heat pumps, a 3x5 array of heat pumps. And if you look at the valve arrangement on the left, you'll see it's identical to what we've been discussing. These are switched around so that the above ground unit is now on the far left rather than at the bottom. But the two valves and the two water pumps and the 3 valves are just identical to what we had in the previous design. Pardon me. So right here now, instead of a single heat pump, which was in this region, we have a device which is called the Twin T fixture. And this is it's a passive device. It has 4 water connections. It has 2 relatively small pipes coming in horizontally here, and 2 larger pipes that are coming in the vertical path. So it's kind of like what's called a hydraulic separator. It allows a different flow rate on the left-hand side compared to the flow rate in the vertical path pipe here. And that's very beneficial. So basically, hot water or cold water can come in from the left-hand 3 blocks, and they will condition the water that's in the vertical pipe. And so that that vertical pipe can have a large diameter and a large flow rate, and it can flow through this, what's called a reversing valve. It can flow through this block right here, and it can go either up or down. This four-way valve right here is called a reversing valve. And this water pump is the pump that causes water to flow either up or down in this path. And so let's assume the water is flowing upwards in this path. And then it enters in a pipe right here at the upper right in this design, and it flows into this what's called a header pipe. And it flows through 3 additional valves that are computer controlled to make sure that we have an optimum flow rate in all 3 of these paths. So now the water will flow in a single pipe coming down this way and this way and to the right here. And each of these heat pumps will get either relatively warm or relatively cool water for providing whatever the building needs. Now, the purpose of this reversing valve, getting back to that, is if we do nothing, if we do not have a reversible flow capability, then, and we have clockwise flow in this, what's called the primary loop, where my mouse is going now, it's called a primary loop. And the heat pumps each have their own small secondary loops. But if the water is always flowing clockwise in the primary loop, then the heat pump at the top, the 3 heat pumps at the top in this design will always have the very best temperature and the highest efficiency, and also heat and thermal capacity. Because if we're, let's say, in a heating condition, then every one of these heat pumps is taking heat out of the water, and it's making the water colder as it flows down this path. So the bottom heat pumps will always be getting the worst temperature for efficiency. The top ones will always be getting the best heat temperature for efficiency. That's really not fair, and it might cause failure of some of the heat pumps. So what needs to be done, or what can be done, is periodically this flow direction can be reversed. So let's say it reverses once per day or once per week. So when the flow is clockwise, yeah, the top heat pumps have the best result. When the flow is counterclockwise, the bottom heat pumps have the best result. So everybody gets equalized in terms of efficiency and capacity over a long enough time period. This kind of reversal has been done for different kinds of thermal distribution products, but as far as I know, it hasn't been done yet for an array of heat pumps, such as shown here. And there's a lot more engineering work that needs to be done to optimize everything regarding that. So anyway, moving along. Now, suppose we want to couple more than one of these primary loops together. There's a way to do that, and that's shown on these 2 images here. Primary loop number 1 is what we were just talking about. You see the reversing valve and the water pump, and we could have flow either clockwise or counterclockwise through that loop. Now, suppose up at the top we have another primary loop, which has the same kind of things in it. Let's say another 15, or it wouldn't have to be 15. It can be any number of heat pumps and or chillers that are being fed from that primary loop. So to couple them together, we're proposing that a donut type device be used for this coupling. And an enlarged view is shown on the right here. It's very simple. We have 4 equally sized pipes that flow in the east-west, north-south configuration. So the example with the arrows on the right here are such that there's clockwise flow in this bottom primary loop. The water is coming in. You see the arrows here. Water is coming in this way, flowing out this way. So we have counterclockwise flow in primary loop number 2. Water is coming this way across, down here, and then up. And you see the arrow coming up here. So basically, the way this works is when we have an equal flow rate in those 2 primary loops, then all of the water from primary loop number 1 has to flow into primary loop number 2. It cannot flow in directly across. It has to flow all the way through primary loop number 2, and then it comes back and gets back into primary loop number 1. So if you have a molecule of water that you're trying to follow through both of these loops, it's going to go through both loops before it can get back to where it started. And what this means is if you have a source of heat in one of these loops, let's say it's a laundromat, or it's a computing center with lots of computers generating heat all year long. That heat can be shared with every single heat pump in both of those loops, which is a very good feature. So anyway, this looks kind of interesting as a way to combine the loops. Moving along now to something much different. Instead of boreholes in the ground, which we've been talking about, suppose we have a water pit. And it could be a natural lake as well. This is done quite a bit with ground source heat pumps. People put a heat exchanger at the bottom of a pond or a lake, and that works. You have pretty good stable temperature. But not everybody has a pond or a lake nearby that they can take advantage of that way. But if you go to Denmark, you'll find a number of examples that are kind of like this design. And they call it pit storage. It's a water pit, actually. It's excavated, and the earth that's dug up, they just pile up around the perimeter, which has the name dam here. It's a dam on all 4 sides, actually. And then at the top, they have a floating insulated cover. And that's a very important part of this design. And then they have a very large array of solar thermal collectors, so that all summer long they're collecting heat from the sun, putting that heat into the water pit. And the array of collectors is so large that they can get close to the boiling point of water, believe it or not. So at the end of the summer, they have temperature near the top of this water pit that's close to 200 degrees Fahrenheit. So they've got to insulate that so that heat doesn't escape. So that's the purpose of the floating insulated cover at the top. That's a very critical design part of this. And in this example, they bring water directly in and out. They don't have a heat exchanger in this pond. They have to take care of filtering, etc. And so then it gets fed off to a number of homes in a town. So a big fraction of the wintertime heating is not done with natural gas or anything else, or even much electricity. They just use water pumps, and they pump nice hot water from this pond directly into a whole lot of buildings, maybe hundreds of buildings in a given town. So this works. It's done quite a bit, but mostly in Denmark. So we're thinking now about a modification of this Denmark example, and this is one possible modification. In this case, instead of having water directly pumped in and out of the pond or pit, we're showing a heat exchanger in the central region here. And this heat exchanger can be a flat panel made of stainless steel or plastic. There are examples of both of those. So this is a water-to-water heat exchanger. And you now have nice protected fluid or